and welcome back to another lecture of Stat 479 time series analysis. Now we're really going to get into the meat of the course when we look at the ARMA model. So the ARMA model is made up of an AR, an autoregressive, and an MA, a moving average process. We're going to look at these in very fine mathematical detail and figure out exactly how they work and what we can learn from them and how we can model time series data using these tools. And they are really going to be the building blocks for our time series models. And welcome back to another lecture of Stat 479 time series analysis. In this lecture, we're going to be looking in detail at the mathematical properties of the AR, the MA, and then the ARMA and the ARIMA process. So these are really going to be the building blocks for our statistical model. And before we look into things like estimating, fitting them to the data, what we want to do is we want to understand these types of stochastic processes, these time series models, in a little bit more detail first. So that's what we're going to do in this lecture. So the overview, right, and this is section 2.3 in my lecture notes. And the overview is the idea is we're going to look at ARIMA models, but we're going to start with all of the, I'm in blue. Let's try that again. All right. So what we're going to do is we're going to break this into pieces and try to figure out what each piece is doing, because we haven't actually discussed what an ARIMA model is yet. So the first thing we're going to discuss is the AR piece. But before I get into that, what I want to say is that effectively what we're trying to do is we're trying to write some sort of equation to understand what X is going to be, or what our time series process is going to be doing. And there's many different ways that we can do that. The first here is going to be our autoregressive process, or the AR process. So we did see this already, but now we're going to go through it in a little more formality, let's say. Because what we can do is we can define XT to be be an AR process. I should say an ARP process, so a pth order autoregressive process. And we're going to say that XT has mean 0. This is more for convenience sake. We'll talk about that in a second. It just makes it a little bit easier to assume the mean is 0, so we don't have an extra term flying around our equations, which gets annoying. And we write XT in the following form, which is going to be WT, the white noise at the current time, plus a summation of, we'll take I from 1 to P of, now I'm going to use the coefficient phi, because the thetas are going to come back in for the moving average piece. So the standard notation, as you might see in textbooks or other places, is to use phi for the autoregressive coefficients. Anyway, I should finish the equation, which is going to be T minus I. Yeah, and WT is white noise as usual. I should just point out with WT white noise with variance sigma squared, just so we have that there. And I should say these are the coefficients for our model, or our process here, phi 1 through phi p, which are all going to be real numbers. Some of them could be 0. Usually we would enforce, right, that the largest one, or the one with the largest index, I should say, that is phi p, is not 0. Otherwise, it wouldn't be a pth order autoregressive process. It would be a p minus whatever. So that's just sort of a subtlety here. But yeah, effectively, you can have any phi's that you want. Now, sometimes you will get a nice, well-behaved stationary process. Other times you may not if you pick the wrong values. So one we're going to do is look to see what happens with different values of phi, and then eventually we're going to look into actually estimating them from the data. But at this point, we're just going to kind of forget about data for a second. Again, there's a lot of buildup in this course with actually looking at the mathematical models before we can work with real data. There's also a more convenient way to write this in terms of what is called the autoregressive operator. So what that is going to be, if I can get that thing out of the way. So what we're going to do is we can actually write this in terms of the backshift operator. So I'll say for B, the backshift operator, that one that I talked about, I think in two lectures prior to this one, what we can do is we can define operator. We can define the autoregressive operator. So the autoregressive operator is going to be capital phi of B. And the point is that we're going to apply that as an operator. So the operator, remember, acts on the time series xt. If I apply the backshift to xt, I get an xt minus 1 out. The way that we're going to do is we're going to rewrite our equation. I should say we're going to rewrite this equation up here as capital phi of B applied to xt is equal to wt. So this is going to be a nice shorthand notation. And it's actually going to be convenient because this phi, capital phi, that is going to be very important. So here, I'll say where capital phi of B, I want to use B. Yeah, we'll just use B for now, is going to be a polynomial in B. So it's going to be 1 minus the sum. Now we're going to take I from 1 to P of phi sub I and B to the ith power. So remember, the more times we apply B, the more we shift our time series back in time. So I didn't really do anything here. All I did was take the summation here and move it to the other side of the equation. Let's do that over here. And then rewrite the sum of these x's, these xt's and xt minus i's, in terms of some more abstract operator notation. But this thing is actually going to be quite important in a minute. So it's why we like to write it this way. Also, it just helps because when we start putting in other pieces like moving average pieces, the I is the integrated part, which is a bunch of differences. The equation for one of these can be very, very messy. So it's quite nice to use the shorthand. Now, one thing I did want to mention is that I said at the beginning that we assume that the mean is 0. Well, we do that more so for convenience. We don't have to, it doesn't have to have a 0 mean, but the point is that we can always write it in such a way that it's just in a 0 mean way. So let's just try that really fast. So let's say if xt has mean mu, whatever mu is, just some number, then we can write xt as x tilde t plus mu, where x tilde t is mean 0. Okay, well, that's fine, right? We're basically saying we can subtract off the mean and we'd get a mean 0 process. But if we want to look at that in terms of the autoregressive formula, the one up above, the first green arrow up at the top of the screen, well, what we can do is we can plug this definition in and see what happens.
So what we get is that if we, let's say just ran off the top of the screen, there it is. If we try to apply this definition here, what we end up with is an x tilde plus mu, and that's going to be WT, but we're going to also add in this summation here, I from 1 to p of phi I, and then we're going to replace xt minus I with x tilde t minus I plus mu. So all we're doing here is I'm replacing the x's with an x tilde plus mu. Why? Well, what happens is that we can reduce this down to, well, basically I put the mu, I subtract mu from both sides, and I collect all the mu terms together, and I get something that's going to look like this, which is 1 minus the sum, I from 1 to p of phi I. I guess that's just it, phi I. And then I have all the other pieces, which is the WT plus the sum of I from 1 to p of phi I xt minus I, but that's an x tilde. So what did we do here? Well, what we said is basically I have, if my xt does not have a zero mean, then it can be written in terms of a mean zero process with some extra constant added on. This is a constant term. And the other things underlined in red here is just going to be the same definition that's about to fall off the top of the screen here, just with x replaced with x tilde. So all it's basically saying is, yeah, we can shift a process by some mean mu, and the definition still works. It's just that we'd have extra terms to throw around, and it would get a little bit messy. So for convenience sake, we typically just kind of ignore that and just say, okay, let's just assume it has mean zero. It's actually very common in statistics, even in research, to see people just say, okay, assume the mean is zero, assume in regression context the intercept term is zero, because these things are there because they have to be there, but they're kind of annoying mathematically to work with. So if we can get away with just setting them to zero, it's just nicer. So the next thing I want to talk about is the idea of causality. We'll say causality for an AR process. So we have some intuitive idea, right, of what causality is. Causality says that the past is going to influence or have some influence on the future, right? Whereas the future is not predicting or influencing the past or the present, that is. So we have this idea of an arrow of time, and causality says that the past, influences the present and the future and so on. So we can consider this in the AR and an AR1 process, just for simplicity's sake. So I'll say recall the AR1 process, which is just xt. In this case, I'll use phi 1 to keep with the notation from above, xt minus 1 plus wt. Now, when you look at that, you might think, well, that sounds causal, right? Because the current time point t depends only on the present and the past. That is, it depends on wt, which is our present white noise, and it depends on xt minus 1, which is what happened one time step ago. So it's like saying the price of, say, a stock or something is influenced by the price yesterday and some random fluctuation. But that only makes sense in the case that we'll consider when phi 1 is in magnitude less than 1. And we looked at this before, that implies stationarity. So let's look at that process again. Well, we know from what we looked at before in these in this course that if phi is less than 1 in absolute value, or phi sub 1 is less than 1 in absolute value, then what I can do is I can rewrite this process in terms of a linear process. Here I is going to be from 0 to infinity, and we have phi 1 to the ith power and w t minus I. So the idea is that this guy here is a causal linear process. So it only depends on white noise that goes into the past, right? Which is why it's causal. Basically, this is t minus 1, t minus 2, etc. When we first looked at a linear process, you could index it into the past and into the future, then it would be non-causal. But at least in this case, we have this nice causal representation. So that's nice, but what happens when phi 1 is greater than 1 in magnitude? We'll say, but if my coefficient is greater than 1, well, we know from before that there's a problem that we don't have that station, or actually, no, there's even more problem than not the stationarity thing. Sorry, that's when phi is equal to 1. We know when phi is equal to 1, we have a random walk and it's not stationary. But we never really considered what happens when phi is greater than 1 in magnitude. So maybe I'll just write that in we'll just squeeze in that. I'll say when phi is equal to 1, we have a random walk, which is a very special boundary case, and it is not stationary. I can't write it in terms of that linear process. The whole thing would have infinite variance if I tried to take this thing into the infinite past, that is, take I to infinity. So that's sort of point number, that's the little middle case. But what happens if phi 1 is greater than 1? And now things get, a little weird. So let's stick with me on this. So we looked at this in some data settings. If I try to simulate a process, even if phi is just a little bit bigger than 1, this thing blows up exponentially. It explodes because instead of multiplying by a number, having a geometric series where I'm multiplying by something less than 1, so we sort of decay geometrically. If phi 1 is greater than 1, now I'm multiplying itself by itself. I'm blowing up geometrically, and that's bad. But we can still try to understand this as a non-causal linear process. So how do we do that? Well, we can apply the definition of this process. And what I can do is I can say that xt plus 1 happens to be, well, what? Phi 1 xt plus wt. T plus 1, sorry, wt plus 1. Okay, so now if we rearrange the terms in this equation, we could actually write this as xt is going to be phi 1 inverse xt plus 1, and then we have to subtract a phi 1 inverse wt plus 1. So now what we're saying is that xt can be written in such a way that it depends on the future value xt plus 1. Okay, not great for statistics because typically we want to use the past, which we know, to predict the future. But mathematically, we can do this. And there is going to be a kind of a point to this. It's not just mathematical nonsense. But let's keep doing this iteratively and see what happens. So if we continue recursively, as I did in some of the early lectures, and as you would have done in assignment 1, when you had to compute things like autocovariances, then what we can do is we can plug in this same definition and we can actually get an xt plus 2 in here. The point also to remember is that phi 1 is greater than 1 in magnitude. Therefore, its reciprocal, phi 1 to the minus 1, is going to be less than 1 in magnitude. So maybe I should write that in on the side. We'll say note, phi 1 inverse is less than 1 in absolute value or in magnitude, which is good because it means our infinite series is actually going to converge in sort of a probabilistic sense, I guess. What are we doing? Yes, so we have a t plus 2, and then we're going to have a phi 1 minus 1 w t plus 2. And then we have to take, so this, right, this guy is this, and then we also need to have this last piece here, which is going to just be the same thing, phi 1 minus 1 wt plus 1. So if we kind of rearrange the terms a little bit, we get a phi 1 to the minus 2. I should probably just write phi and drop the sub 1 because it's just kind of annoying to keep writing, but that's okay. The point is that we could have an AR process with more than one term in it. We just don't in this case. And then we're going to have minus, and then in the giant minus bracket, what we're going to have is a phi 1 to the minus 2, wt plus 2, and a phi 1 to the minus 1, wt plus 1. So what we're going to do is the exact same thing we did for the causal AR1 process, the one above, where we just keep iterating until we get an infinite series. And if we say ... keep iterating this thing, well, the first term is going to end up being 0 again, because we keep multiplying by a number less than 1 in magnitude, which is going to take this down to effectively a random variable with 0 mean and 0 variance. So it's 0, I guess, almost surely, or whatever. It's 0. And then what we do is we take I, now from 1 to infinity, phi 1 to the minus I wt plus I. So there's a couple things going on here. First of all, this series actually makes sense mathematically in the sense that I'm summing up a bunch of independent or uncorrelated or independent white noise piece random variables. And because phi to the minus 1 is less than 1, this thing will actually converge. So what we actually have here is a non-causal linear process. And here the index runs t, I guess, t plus 1, t plus 2, t plus 3, etc. So this actually can be thought of now as, well, actually not thought of. It's what we have is something that's a stationary process. Well, okay, we don't know exactly that it's stationary. We just see it and we say, well, this looks basically mathematically equivalent to the one above. The only difference is the one above is causal. I'm running my series into the past. This one is non-causal. I'm running it into the future. So what we really need to do is compute the autocovariance to show that it is in fact a stationary process. So let's do that. Because I know that it's stationary, what we're going to do is we're going to write it as kx tau, where tau is going to be the difference, right, between two time points. And what we can do is we can write this now as the expected value. And again, when we're computing the autocovariance, we're multiplying two of these infinite series together. So when we do that, we end up with a double sum. We're going to take, I guess the two negative signs cancel out. Yeah, because we'd have minus and minus. So we're going to take, let's say, I from 1 to infinity, and I guess j from 1 to infinity. And then we're going to have two different pieces here. Well, I guess there's two things we're going to have. We're going to have a coefficient of phi 1 to the minus I. We're going to have a phi 1 to the minus j. We're going to have a w, let's say t plus j, and a w t plus tau plus I. So yeah, here we have, again, our two time series, or our two white noise processes. And once again, the nice thing is that this expectation, even though it's over a double sum with, I guess, an index going to infinity, this whole thing is convergent. I can move the expectation inside of the summation. And when I take the expectation of the product of two white noise terms, it's always going to be 0 unless the two indices are equal to each other. So what I get is my sum over I. I'm just going to write I and j here from 1 to infinity for shorthand. I can collapse the phi minus I minus j together. And then I get something that's going to look like sigma squared, the variance of the white noise process, and an indicator function, which is t plus j is equal to t plus tau plus I. Right? Because that's the only setting when this thing is going to be not 0. And then from there, we just kind of, fight our way through the equation. The t's cancel out here, so we don't need those. And we're just saying that we want, effectively, if we rewrite this, what we end up with is something like j minus I is equal to tau. So what does that mean? Well, that means that if we were to, how do I want to write this? Well, what it means is that if I were to, this part's always a little, make sure I don't miss any terms here, okay? Because what I ultimately want to do is I ultimately want to take one of these towels out of the I minus j, or minus I minus j. So what I want to do is I want to write minus I minus j as, I guess, j minus I, let's see if we can do this, minus 2j. Did I do that right? I think I did that right, because what ends up happening then is that I can replace that first guy with a tau minus 2j, something that looks like that. Yeah, I think that's good. It's pretty easy to mess up these calculations, so make sure to keep track of me. And I guess you can't yell at me while I'm doing a pre-recorded video, but definitely let me know if I messed something up. Anyway, the point of that kind of strange comment is that when I have this sum, what I want to do is I want to take a tau. Well, I want to take two things. First of all, we have a sigma squared, which is just floating around there doing nothing, but being multiplied by every term in our sum. So we bring it outside of the summation. Okay, that's good. Then what we're going to do is we're going to extract. Yes, I did it slightly backwards. What I actually wanted to do was I wanted to extract not tau, but I guess minus tau. I want something that's going to look like this, and I want that minus sign there. So what I need to do is slightly rearrange the way I was writing that, because what I ultimately want is not the 2j, but I want a 2i. So, man, these terms, I tell you. What I also actually need to do is I need to flip this. I told you these things are a mess, right? Tau, we have minus tau is going to be I minus j. And then what I need to do is I need to take out write this thing, or sorry, write. And then what I would need to do is redo this second line and write minus I minus j as minus 2I, I guess in this case minus tau, or something like that. Yeah. Minus 2I up in the exponent there. Yeah, the manipulations can be quite tedious in time series. The reason that I'm trying to do all of this is so I can sum up this last guy as a geometric series. Let me highlight that in a better color. So this thing in blue here is a geometric series. So what I end up with is, well, just sigma squared. I'm going to have a phi 1 to the minus tau, and I'm going to divide that whole thing by 1 minus phi 1 to the minus 2. So there's tons of negative exponents floating around. But remember, phi is greater than 1. So in this case, phi to the minus 1 is less than 1, and therefore our geometric series converges. But most importantly, the autocovariance tells us that this thing is stationary. And we're back. I lost the video there for a second. I was just too wrapped up in these wonderful, tedious calculations. And what I wanted to end with was the fact that this geometric series is slightly different than our other geometric series. This geometric series starts with I is equal to 1. And because of that, we have one more term that we have to add in to our autocovariance, which is going to be something like this in the exponent. Okay, now we have our wonderful autocovariance. It only depends on tau. This whole process is stationary. So actually, so if phi 1 is greater than 1, we have a stationary process, which is cool, but it's not causal. Oh, that's too bad. I guess it's not causal, so it doesn't really make a lot of sense unless there's a way to find a causal process that is equivalent to the non-causal process. And we're going to do that because, yeah, this is kind of a bit of a crazy part of the course, I find. So what we're going to say is let WT be Gaussian white noise. Therefore, XT is a Gaussian process. And there's something very special about a Gaussian process. Recall that a GP, Gaussian process, is characterized by its mean and covariance. I guess autocovariance I should write to be precise here. Autocovariance. So the Gaussian process is quite nice in this case because it only depends on, it only matters once you know what the mean is and you know what the autocovariance is, you know what your Gaussian process is. You're kind of done. You don't need anything else. So is there another process that has the exact same autocovariance as that big green one? The answer is yes, and we're going to write it down. So let's now consider YT. And there really is a statistical reason why we're going through all this. So I keep telling you that just to say, stick with me, and we'll get there. So we have YT, and YT we can write down as this process, which is going to be phi 1 minus 1, YT minus 1, plus some white noise process VT. I use V because it's not the same as W. I should say where VT is Gaussian white noise with a variance. It always has mean 0, of course, but its variance in this case is going to be sigma squared phi to the minus phi 1 to the minus 2. So what we do is we basically take that phi coefficient and we divide the variance sigma squared by it. So what we have here is a causal, so the point is that yt is a causal AR1 process. And if we take the time to actually write out, we find that the autocovariance of y at lag tau just so happens to be something that's going to look like sigma squared phi 1 minus tau phi 1 to the minus 2 divided by 1 minus phi 1 to the minus 2, which you can use just based on the formula that you would have done back in the earlier notes, or I think we did it in assignment 1 as well as earlier in the notes. So the point is that this process y is the same as this process x up at the top. If the white noise is Gaussian, they are equivalent, I guess stochastically equivalent, in the sense that they will have the same distribution for any finite collection of time points. And that would be, I guess, a multivariate Gaussian distribution. All right, so that's a little weird, right? Because what we're basically saying is even if we have a non-causal process, there is an equivalent causal version of that process, at least in the case that the white noise is Gaussian. If the white noise isn't Gaussian, we don't have this nice equivalence. But there's something important here, which is important for statistics, which is why I was going through all this craziness, is that if we have xt is equal to phi 1 xt minus 1 plus wt, which is our non-causal AR1, and if we have yt is equal to phi 1 inverse y t minus 1 plus vt, which is going to be our causal. Well, if I have data that's coming from a process that looks like this, what am I going to be estimating, right? Am I, because ultimately we would want to try to estimate this. We would want to put some hat on there and say, I estimated the AR1 coefficient, or I estimated, say, the variance here, like sigma hat squared. But we have two different processes that have the exact same behavior stochastically, so we can't actually differentiate between the two of them, right? Well, that's a problem for statistics. That's called identifiability, right? When in statistics, we want to make sure that if we have data and we have a model, it's only one model is going to represent that data in some sense. Here we would have two models that are exactly equivalent in every way, except that one's causal and one's non-causal. So what do? What we do is we cross out the non-causal one and we say, you know what? We live in a causal world, at least as far as we can tell. So we typically want the past to predict the future. So when we try to do estimation for an autoregressive process, we only estimate causal models, or in the case of the random walk, we may get a non-stationary model. But that's just an important little note to take into account. because it can be, it is kind of a strange occurrence here, but something that is certainly important when doing statistics. You want to make sure you know what you're estimating. So if we had data from this process, we'd be estimating this coefficient here, that is phi1 inverse and not phi1. Okay. So we can actually extend this idea. So I'll say now, let's look at ARP, the ARP process. Well, if we go back to our original notation, then what we had was something that looked like capital phi b applied to xt is equal to wt, where capital phi is our autocovariance operator. Okay, so operators are invertible, I guess, in some cases. So in this case, what we can do, and we'll define it better in a second, is write this as phi inverse b applied to wt. So this is going to look a lot like a linear process in the sense that I'm applying some type of operator to wt. But now we have to ask the question mathematically, does phi inverse exist or make sense? Right? If I say I have a matrix and I want to invert it, well, it may not exist. There may not be an inverse. So in this case, we need to consider that. Is there actually an inverse here? So now, again, we're going to go back to the AR1 process because it's the easiest thing for me to write down to give you a concrete example to look at. So if we look at the AR1 process, this one's a little bit easier to look at. What we would have is that phi, my capital phi of b here, is going to look something like 1 minus phi 1 b, based on the definition from the beginning of the course. Now we're going to get into complex numbers because you probably thought you wouldn't need them, right? When you learn them in whatever, I guess, pre-calculus or something. But yeah, we have to use a little bit of complex numbers to make sense of this. So we can say let z be a complex number and consider capital phi of z being 1 minus phi 1 z. Okay, so this is just is that a monomial, I think, or it has just one term in it. I forget my, I think it's monomial. I need to double check my terminology to make sure I'm not leading you astray here. But what we have here is we have phi z is just going to be a polynomial in terms of z, some complex number. Okay, so note that phi inverse z can be written, right, as 1 over 1 minus phi 1 z. Okay, that's just take the reciprocal. And then the question is, does that make sense? Can we divide by that? Well, sure, yeah, we can definitely divide, but can we write this in terms of an infinite series? And the point is that we can write this as a geometric series that looks like j from 1 to infinity, phi 1 to the j, z to the jth power. And this is going to have a radius of convergence, if you think of it in terms of like a power series, right? If you recall, right, the radius of convergence is the values that z can take such that this series converges. right? If z is really, really big with respect to the value of whatever phi1 is, then this series will not converge, and we can't write it down. It doesn't really make sense. But here we're going to have a radius of convergence of phi1 to the minus 1, which basically is to say, let me make sure I have my notes here right. So what that means is that, therefore, the series converges when our z here, I guess in magnitude, because it could take on any complex value, is less than phi1, the absolute value of that thing, which I guess we're assuming is real valued, but could be negative. So we need an absolute value nonetheless. So, okay, why are we doing all this? Well, if phi1 is less than 1, then what we can do is we can use this this idea, this series here, and replace the z with a b. We can use, I'll say the green box here. We can use this thing, but what we can do is we can replace it, z, with a b. And what we write is we write that xt is going to be, well, the same thing that I have the other green arrow pointing to, which is phi inverse b wt. And if we have that convergence property, we can replace phi inverse with 1 minus the sum j from 1 to infinity of phi 1 jb to the j with a wt. And then we can actually just, well, I guess decrement it if we want, and we end up with our linear process again, which is going to be wt minus the sum j from 1 to infinity of phi 1 to the jth power wt minus j, because it's being backshifted j times. All right, so that's like a quick kind of shorthand to get back to the linear process that we had back in lecture 2, or I forget, I think it was 2. Maybe it was 3. Right. So again, this is, again, a lot of kind of craziness with the idea of using the complex numbers. But what we're really doing is we're just saying if we treat this, if we take this polynomial phi, we shove in a complex number z, then we can determine whether or not this inverse exists in terms of a series, or at least it exists, what it looks like as a series, assuming where z is smaller than the radius of convergence. Now, we can extend this to the ARP process. And what we can do is we can rely on a fun little tool, the fundamental theorem of algebra. So for an ARP process, right, what we would have is something that looks like my autoregressive operator here is going to be, I think I was using I forget. We'll just use I from 1 to p of phi sub I, because we could have multiple coefficients here, and b to the I. Now, if we were to write this in terms of a phi applied to a complex number z, well, I'm going to get the exact same thing. I'm just going to replace b to the ith power with a z to the ith power. And because of the fundamental theorem of algebra, it says that if I have a polynomial in the complex plane, it factors, so I can write it as the product of a bunch of monomials. In this case, what I get is, well, something that's going to look like, I guess there's a couple things I need to do here. Yeah, the first thing I need to do is factor out the phi to the p. And then what I'm going to get is a bunch of z minus r1, which is the first root, z minus r2, the second root, all the way up to z minus rp, the pth root. Now, I should say where, just to make sure it's explicit, r1 through rp are the roots of this polynomial, and they may be in the complex plane. Because, again, we need to work in complex numbers so we can completely factor this polynomial. All right, so we're almost there now, because what that means is that, yes, so what we first want to say is note that minus 1 to the p times the phi p times the product j from 1 to p of r j is going to be 1. So why is that true? Well, it's because if we go back up to our if we go back up to this equation for the polynomial here, we know that the constant term here, the one that has nothing to do with z, is a 1. So that 1 has to be the product of all of these pieces, all of the roots times phi p, the coefficient that I pulled out of the front, have to multiply together with the minus 1s coming in because we don't know if p is even or odd, have to multiply together to get 1. And that means, therefore, we can write our phi inverse of, let's say, z. That should be a minus 1, so let's write that again. So this thing now can be rewritten as 1 minus r to the minus r1 minus 1. So this is the reciprocal of the first root, and then we're going to multiply by 1 minus r all the way up to p minus 1z. And the point is that all the other terms multiply together to get 1, which is why there's this 1 is this 1 on top, which is the point of this kind of silly thing I wrote about the product of all these things being 1. Okay. Therefore, if all roots are say, are greater than 1 in magnitude, then, that is, they lie outside the complex disk, or the complex, I guess, yeah, disk is probably the right word. Then we can take that phi b xt equal to w, our autoregressive equation. We can rewrite it as xt phi inverse bw, and we can actually get an expression for what phi inverse is and what it's going to look like. I'll just write it down on the next line here. Is going to be the product over the pth, we'll say j from 1 to, I was using I before. Yeah, we'll switch it and hope that I don't make a terrible mistake here. We have I from 1 to p. Oh, there's a typo in my notes. I'm going to have to correct that. just an omission, because what we're going to do is we're going to have to take j from 1 to infinity of r. Let's see. What are we doing here? We're taking r. Yeah, this whole equation is needs to be fixed. What we would need is we would need ri, the ith root, to the minus jth power. One of the reasons why I'm assuming the roots have to be greater than 1 in magnitude is because I have these reciprocals. I need the reciprocal to be less than 1 in magnitude so that we can sum a geometric series. And then we're going to have a b to the j here. And this is all going to apply to wt. Okay, so that's kind of a mess. But what it really is telling us, right, is that we can take each of these, I'll underline it in blue. So each of these pieces here in the denominator of this, the reciprocal of this polynomial here, each of those, if the root is greater than 1 in magnitude, can turn into a geometric series, which becomes one of these, one of the I from 1 to p of one of these terms. So effectively what we're doing is we're doing the same thing we did up here at the top of the screen for the AR1 process, but we're doing it p times and we're multiplying p of them together. All right, so that's a ton of writing and equations. All right, so we just went through this big mathematical derivation to effectively write an ARP process in this form at the bottom of the page. So then the question is, well, why? Well, the idea here is that the main takeaway, besides all the fun with mathematics, is that if the roots of this polynomial phi of z, the roots are I guess, well, we'll just write it out, ri greater than 1 in magnitude, then we have a causal process, a causal AR process. And this is going to be important because ultimately when we look at tests, so if you happen to read, we talked a little bit about testing for stationarity with things like the Dickey-Fuller test, which we'll do in more detail later. But if you just happen to glance at the documentation for some of these tests, like that one, for example, but other ones as well, they'll say something like, we're testing for the existence of a unit root or or something like that. So the point of that unit root that they keep talking about is coming directly from this polynomial. It's basically saying we want all the roots to be bigger than 1 in magnitude. We don't want them to equal 1. If the roots are less than 1, then we have that non-causal problem, and we have to reverse it to get back to a causal process. So typically the roots here are always going to be either greater than 1 or, I guess, equal to 1. If they're less than 1, it's non-causal, and there'd be an equivalent causal process where the roots are greater than 1. Yeah, time series is kind of a mess, right? But regardless, that's the main idea. Anyway, we are not quite done yet, because the next thing I want to talk about is the moving average process. And I think we have enough time to get through this. I guess I have as much time as I feel like, but I will try to keep it to approximately the normal, sort of 80 minutes of class time. So we can consider a moving average process, the MAQ, a qth order moving average, and we're going to do so in a way very, very similar to what we did with the autoregressive process, but we don't have to deal with all those crazy roots for the time being. You'll see what happens. Anyway, we can write our moving average process as a sum of white noise kind of backshifted into the past. So what we have is we have the usual setup. Here we have J from 1 to Q. We have theta, just so it doesn't conflict with the phi's that I was talking about in the previous section. Theta T minus J. And we assume, again, such that theta 1 through theta Q are going to be real numbers, and we typically would want theta Q to not be 0, so that it is a qth order moving average process. Now we can write this once again using the notation capital theta for our moving average operator, where this guy here is the moving average operator. All right. And just to, I guess, explicitly write it down, capital theta of B is just going to be, well, very similar to the autoregressive piece, but it's going to be a 1 plus, because we're not moving anything to the other side of the equation like we did in the AR process. It's going to be a 1 plus the sum J from 1 to Q of theta J B J. All right, and this is our moving average operator. Okay, so we can proceed similarly, but once again, if we wanted to do statistics, we would have data that would presumably come from, say, a moving average process, and we'd want to estimate it. We'd want to say to ourselves, okay, I want to estimate the thetas, so I have to make sure the things that I'm estimating are unique or identifiable in a statistical context. And yet again, we run into another uniqueness problem, much like the causal non-causal issue above. So up here, for the AR process, we had the problem of causal versus non-causal. Down here, for this guy, we're going to have the idea of invertible versus non-invertible. So we're going to have a similar issue where we have to deal with the fact that there are equivalent versions of the moving average process that will not be invertible or that will be invertible. Of course, I haven't told you what that is yet. So let's consider, again, a simple example, which is going to be the MA1 process, because having more terms just makes everything worse when I try to explain it. It's hard enough keeping track of all the terms when I just have an MA1 or an AR1. So let's see if we can get through this one. Anyway, what we have is something like this. We have a WT and we have a theta 1, WT minus 1. Now remember, the MA process, you can think of it as kind of like propagating the noise through time. So if at time t minus 1 there was some shock to the process that we're looking at, the price of our stock just happened to go up or go down, then the point is that shock will still kind of be present one time step later, but decremented or multiplied by some value theta. I'm saying decremented because typically we would want theta to be less than 1 in magnitude, though it doesn't actually have to be the case. So let's look into that a little bit closer. Well, we know from I don't think I did this in the previous lecture, but you would have done it in your assignment, that if we compute the autocovariance for this thing, the autocovariance is fairly nice. It's just going to be theta 1 squared sigma squared, and this is tau equal to 0. We have theta 1 sigma squared tau equal to 1, and we have 0 for all other values of tau. So this thing is going to be a stationary process. This is stationary for all theta 1. So we don't have to worry, like in the AR case, when our coefficient equals 1 and we end up in a random walk setting. In this case, well, we could have theta be kind of whatever it is. We'd still have a stationary process, so that's good. But like with the AR process, just because we have a stationary process doesn't mean it's nice, in the sense that before we could have a stationary non-causal process. That's not good. And once again, we can also consider the process yt. You can kind of guess where I'm going here. I'm going to write down something that's going to be mathematically or stochastically, I guess, equivalent, if we want to say it that way. Not wt, vt minus 1. Another typo. I really got to work on these notes. Where I should say vt, I'll just write the variance, where the variance of vt is going to be theta 1 squared sigma squared. And if we do that, then it turns out that the autocovariance of y at tau just happens to be the same as the autocovariance of x at tau. Great, so now we have two different processes. They're two different in the sense that they have different coefficients in front of their moving average term. So the problem, once again, is that if we had data, we would want to try to estimate theta 1. But are we estimating theta 1, or are we estimating theta 1 to the minus 1, the reciprocal of that? And once again, yeah, that's going to be a problem statistically. So what we want to do is we want to pick the invertible process. So then the question is, well, what is invertible? Well, it's going to basically do what we did for the AR process, but do it backwards. What I mean by that is that so we want to pick the, I'll say xt or yt that is invertible. And what I mean by that is that if we consider that, let's just say xt, for the sake of writing one of them down, is going to be theta b applied to wt, then we say that it is invertible if we can, well, invert theta. And we get theta inverse b xt equal to wt. So the point is, it's invertible if my theta is invertible. And in this case, or I guess in this setting, right, it's really just doing exactly what we did above. So the point is we can do as before with, say, considering theta applied to some z, for z a complex number, and then we can proceed working through that to determine, well, do we have a power series representation whose radius of convergence is at least 1, or are the roots, I guess, is it big enough or small enough? We want the roots to be the roots need to be large. They need to have magnitude greater than 1 so that their reciprocals are less than 1 so that our series works. Yeah, there's a lot of little pieces floating around here. So for our MA1 process, what we have is two different ways we can write it. We can write WT for X is going to be the sum, and this is going to be I from 0 to infinity of -1 to the I theta 1 I X T minus I. Or we can have WT equal to the sum I from 0 to infinity of -1 to the I theta 1 to the minus I, there's the difference, and then YT minus I. Okay, so the only difference here in some sense is the fact that one of these has a minus I and one of these has a plus I as its exponent. And what that means is that the point here is that, assuming theta is not equal to 1, then either theta 1 is less than 1 or theta 1 inverse is less than 1, which means that one of these series makes sense mathematically, that is, it converges in a mean squared sense, and one of them doesn't. So effectively, the point is we pick the series with coefficient less than 1 in magnitude. And that's going to be the process that we're going to work with. That's going to be the invertible one. If we are in this special case where theta is equal to 1, this is not invertible. So typically, we never want anything to actually be 1. I mean, in a way that would make things very strange too, just because it's almost like there is no. You'd want theta to be less than 1 in some sense, because you don't want the past to be kind of like resonating in some sense and getting stronger as time goes on. You'd want the past to kind of fade into non-existence as you move forward into the future. So if there's a shock to the process, the system that you're looking at, you'd expect that shock to start to dampen as you move away from it in time, not to magnify itself in some strange way. Right. So that's more or less everything that we want to talk about in this lecture, because the next thing what we're going to do is we're going to take this autoregressive piece, the AR piece, we're going to take the MA piece, and we're going to cram them together to get an ARMA model. And now the idea is that, well, I'm just going to write it down just so you know where we're going with this. Next is ARMA PQ, where we take the AR piece, we take the MA piece, we cram them together, and then we want to know, is it causal? Is it invertible? These are going to be important things to know, because statistically we need these properties so that we can actually try to estimate terms in these models, because eventually we're actually going to plug data into a function that's going to fit an ARMA or an ARIMA model, and we need to actually, we really want to be able to actually fit something that makes sense. So yeah, we're going to have one more round of, let's say, crazy coefficient and complex polynomials when we do ARMA and then the ARIMA process. But after that, things will maybe get a little bit better. There's a lot of math in this course before we actually get into the statistics. So what we'll do is we'll do this, and then maybe what we'll do is we'll look into tests for stationarity, because now that we know what these unit roots are, we can actually apply proper statistical testing. And I do enjoy a good hypothesis test, like all of us do. So we'll work on that. But at this point, I think we're done for today. So thanks again for watching. See you in the next video.